So this is, we call this one as I h bar dou psi by dou x is equal to minus h bar square by 2m dou square big psi, okay, I'm trying to write big psi by dou x square plus v of psi, okay. One dimensional Schrodinger equation, okay. Dimension is 1. Even though you have two variables, sorry, speak out. Even though you have two variables, time and space, but in the space it is one dimensional Schrodinger equation. Is that okay?
So V is dependent on x. Is a function of x.
Psi is a function of x and t here.
Potential is a function of x.
Potential can be function of both x and t in the most general case. Both in the most general case. Later we shall talk about time independent potential, okay. In case of two dimension, it would be like this: I h bar dou psi by dou t. Look at here. Here we write it as psi of x comma t is equal to minus h bar square by 2m. Look at here, dou square by dou x square of psi plus dou square psi by dou y square, okay. This is kinetic energy part, plus v of x comma y comma t. If you write v here, v of x comma t. If you write here, v x y comma t, okay. So of psi, okay, where in this case, so this is 1D, this is 2D. In this case, psi is a function of x comma y comma t. Whenever it's a function of two variable, it will be partial differential equation actually. Equation, if equation gives you two variable function, usually that is a partial differential equation, okay. So this is two dimension. Again, in the most general case, v is a function of x comma y comma t, okay. Similarly, I h bar dou psi by dou t, so that's equal to minus h bar square by 2m dou square by dou x square, dou square by dou y square, dou square by dou z square. We call that one as Laplacian. You know that one? Laplacian. I hope you have studied this one. Laplacian of psi plus v of psi. In this case, we write psi is a function of x comma y comma z comma t, or sometimes we write psi of r comma t, r vector comma t. R vector talks about position vector, not scalar r vector. Scalar r means it is your spherical polar coordinate r, okay. R vector comma t. Again, in the most general case, v is also a function of x comma y comma z comma t. Is that okay? 1D, 2D, 3D. Again, we shall first solve 1D problem. Then many cases we just generalize that 1D problem to 2D and 3D, and some 3D problem should be solved, okay. Now look at here. Look at here. What is the interpretation here on psi? Mod psi x comma t whole square. It is probability density. Probability density. What is this one? Mod psi x comma t whole square into dx. What is this one? This was equal to probability of finding the particle from x to x plus dx, okay. I'll write it like this symbolically because I can't write this statement, okay. This probability is always dimensionless quantity. Probability is always dimensionless quantity, isn't it? Now look at here. By taking that idea, this should be dimensionless. Can you give the dimension for wave function? What is the dimension of wave function? Here it is quite difficult to say by just looking into what you call your Schrodinger equation, isn't it? So better to assign dimension for wave function by looking into this one. What is this one? Means psi star into psi dx, isn't it? Psi star and psi have the same dimension usually. If psi has one dimension, psi star will have same dimension. Yes, speak out.
Psi plus should be 1 by length.
Wait. Yeah. So that's what I'm trying to explain. Now look at here. Psi star, these two have the same dimension, okay? When you multiply by length dimension, you are getting dimensionless quantity. This has a dimension. Probability per unit length, that has a dimension. Probability per unit length, it has a dimension of per unit length actually. Okay, but this is dimensionless quantity because this is a probability. So probability in some small region, that's a dimensionless quantity. So that's why using this one, so can you tell me, so if this should be dimensionless, what should be dimension of this? If this is dimensionless, total thing is dimensionless, these two have the same dimension, then what is the dimension of this one? 1 by root L. Why? Into L. This has a length dimension, am I right? 1 by root L, 1 by root L. That's why in case of one dimension, what is the dimension of wave function? 1 by root of length. Is that okay? Quickly, I hope you got the idea.
Yes.
Sometimes if anyone asks very quickly, you should better to go for this one so that you can quickly say. So in case of 2 dimension, can you quickly do that one? The same thing for 2 dimension. Look at here. In case of 2 dimension, if this is the wave function x comma y comma t, okay, mod psi square into mod psi square is probability density, probability per unit area. I better to write this is probability density, means probability per unit length. Is that okay? In case of 1 dimension, it was probability per unit length. In case of 2 dimension, it is probability per unit area. Again, in every case, we call this one as probability density only. Here also we call probability density. That doesn't mean per unit volume, okay? So that's why if it is per unit area, what is this one? Mod psi x comma y comma t whole square dx into dy. This is equal to, this is a probability now. Probability of finding the particle whose x position is x to x plus dx, y position is y to y plus dy. Now psi star psi dx dy. What is the dimension of psi? This total should be dimensionless quantity. These two should have same dimension. So now this should be 1 by L square. When you multiply, you should get 1 by L square, so that you have L square here, L into L, length into length, okay? So that's why if multiplication should be 1 by L square, individual should be 1 by L, 1 by L. What is the dimension of wave function in case of 2 dimension? 1 by length. 1 by length. Is that okay? Quickly see this definition of probability. Now remember, if you rub this out, that's not a probability, okay? It is per unit area. You should multiply by dx into dy. Dx into dy in the xy plane, we call that as infinitely small area. I hope you know that one, isn't it? So similarly, do it for 3 dimension. Okay, mod psi x comma y comma t, z comma t whole square. This is probability per unit volume. This is also called as probability density. This is also called as probability density. Earlier one is also. So now, what is the probability? Mod psi x comma y comma z comma t whole square dx dy dz. So this is, I'll write symbolically, probability that x position, probability of finding the particle, so that its x coordinate is x to x plus dx, y coordinate y to y plus dy. Because in case of 3 dimension, we should talk about all three coordinates, isn't it? Z coordinate ranges from z to z plus dz. Or probability of finding the particle in this small volume, you can say like that. So that's why length cube 1 by something, am I right? Isn't it? Psi star psi dx dy dz. If it is length cube, this is 1 by something. When I multiply, I should get 1 by length cube. That's why this should be length raised to 3 by 2. This should be length raised to 3 by 2. So that when you multiply, you will get length raised to 3. It will get cancelled. Okay? Quickly practice this one later. I hope these are 1D, 2D and 3D. and you should know its interpretation also. Okay, mod psi square, we call it as probability density, but mod psi square is probability per unit length in case of one dimension. It is probability per unit area in case of two dimension. It is probability per unit volume in case of three dimension. Clear? Normalization. Okay, again the same thing can be generalized to 2 and 3 dimension. Okay, whatever we do for one dimension, we just generalize that one to again 2 and 3 dimension. Okay, suppose you have written minus h bar square by 2m dou square by dou x square plus dou square by dou y square. This we are going to define it as px cap square by 2m plus py square or px square plus py square cap divided by 2m, like that. Okay, I hope you can do with these things. Okay, not much big deal, but understanding it in one dimension, that plays very important. Normalization. I hope you read something already, isn't it? So this differential equation will give some solution. That solution will contain some constants, isn't it? That solution will contain some constant. Again, that's why, again, after that solution of differential equation, we started interpreting psi is probability amplitude, mod psi square is probability density, isn't it? That's why normalization is not an inbuilt thing here. You need to enforce that one, okay? Because that Born statistical interpretation came after Schrodinger equation. Is that okay? So that's why normalization is not inbuilt one, because mod psi square is not defined as a ratio like you have done dt by capital T. Am I right? So in your earlier case, in case of both rho of x, in case of classical harmonic oscillator as well as in case of rock which is falling, isn't it? If you integrate rho of x again throughout your region of interest, so throughout the region that particle can travel, you already got one. Am I right? You don't have to enforce that condition. But here you need to enforce that condition. That enforcement, we call that one as process of normalization. Quickly, any doubt?
So in this in this enforcement, is it like the area under the curve 1?
Yeah, mod psi square area under the curve is 1. To make mod psi square area under the curve is 1. Exactly.
Okay.
Dou square psi by dou x square plus v of psi. Okay, now look at here. If psi is the solution, if you multiply some a to psi, that is also solution of the same differential equation. Put a here, a here, because that's a linear differential equation. Is that okay? If psi is the solution, a is also solution. So that's why you are free to multiply psi by a constant, or you are free to change the multiplicative constant, not functionality. If you multiply, again look at here, again suppose you have e power minus x square, okay? If you put 1 here, 2 here, okay, then look at here, so this functionality will not change, isn't it? It is Gaussian, this is also Gaussian, this is also Gaussian. So 3 into e power minus x square, this is also Gaussian, isn't it? Now we need to find such a multiplicative constant whose mod psi square area under the curve is 1. Is that okay? We call it as process of normalization. How do we write? So we write, again we need to enforce this condition, integral minus infinity to plus infinity mod psi x comma t, wait a second, whole square dx is equal to 1. We need to find the multiplicative constant to this function which enforces this condition. Okay, we need to find such a multiplicative constant to psi, okay, which normalizes that function. The process is called normalization. We shall take some example. Yes, tell me. Suppose if I take I'll take this one only, e power minus lambda x square, okay? So my psi is equal to e power minus lambda x square, psi, not rho, okay? Again, again suppose this is a solution. You got a solution. A is some arbitrary constant, okay? Now look at here. What I do here is I'm going to find such a whose mod psi square area under the curve is 1, as you said, isn't it? Now what I do is to find that I'll just put that psi into this one and I'll find that A. Is that okay? To find value of A which normalizes this wave function, I'll put that wave function into this normalization condition. I'll find that multiplicative constant. Is that okay? Just substitute. What will happen? Minus infinity plus infinity mod A square into e power minus 2 lambda x square dx is equal to 1 mod A square. What is this integral? Quickly, anyone? Quickly. Pi by coefficient of x square. So from this one you can find A. Now look at here. A can be plus or minus root of this one. Mod A square is equal to root of 2 lambda by pi, isn't it? Now A can be is equal to plus or minus root of root, am I right? 2 lambda by pi power 1 by 4, isn't it? Now among these two you can take positive root or negative root. Look at here. If psi is the solution, minus psi is also solution of the same Schrodinger equation, same property. It doesn't matter whether you take positive root or negative root, mod psi square is same. You have only interpretation for mod psi square, not for psi. Is that okay? That's why usually most of the case we don't worry about that negative part, we just take positive root. Okay? It doesn't matter. If you take negative root, you will get negative of the earlier function. Okay? If you multiply wave function by minus 1, remember, it will not change any physical situation because all physical situation depends on mod psi square or psi star into psi. Then this positive or negative sign doesn't matter. That's why in this step, take positive root. Simply. You can take negative root also, suppose if you wish. Okay? So this is called, look at here, I found A, okay? We call this, if you substitute back, the function is normalized. That means, that is to say that we are enforcing the condition that total probability equal to 1. Obvious condition that we need, isn't it? Now look at here, we call that one as normalization constant.
So we are not considering the negative part.
If you take negative part, that will not give any new state. That will not give any new solution. Because again, even if you take negative of that one, what is mod psi square? Mod psi square is same then. Only mod psi square have got interpretation, not psi. And one more thing, if psi is the solution of Schrodinger equation, minus psi is also solution of the same Schrodinger equation with same what you call physical situation. That's why changing the sign of wave function will not change anything. So changing the multiplicative constant will not change anything. Is that okay? Whether you take A equal to 1, 2, 3, 4, each and everything is a solution of the same Schrodinger equation. But why we find this A? Because we want to do probabilistic interpretation. Isn't it? Total area under the curve should be equal to 1. Total probability should be equal to 1. Then only you can define probability. Speak up. So again, whatever value put here, that solution, no doubt. The solution of same Schrodinger equation with the same what you call situation, potential, everything. Okay?
But sir, we are considering only psi square, not psi. That's why minus will...
No, again, yeah. So to have this condition, you should find such a, okay, which normalizes this one. You should observe two things. One is, if you change sign of the wave function, even normalization will also not change. Once you find this normalization constant, once you substitute this one, okay, once you substitute this normalization constant to 2 lambda by pi, isn't it? 2 lambda by pi raised to 1 by 4 into e power minus lambda x square, okay? Once you substitute this one, whether if you multiply with minus 1, okay, you will not get any new, again, even then also normalization is followed because look at here, mod psi square, it doesn't matter, okay? One more thing, before this one, if you have any solution, suppose solution is equal to e power minus lambda x square, okay? If you put 1 here, 2 here, 3 here, 2 lambda pi here, all of them are solution. But we choose this one because we had next interpretation, isn't it?
Yes.
Sir, that all will be the only mathematical solution, not the physical.
This process have got physical interpretation. What is that? Total probability should be equal to 1. Otherwise, how do you interpret?
Non-interpretation, sir.
Interpretation. This process of normalization, yeah, mathematical procedure, but it is backed by one physical interpretation. If total probability is not equal to 1, how do you define probability at all, isn't it? Only by looking into psi you can't see. You better to look into, in case of position interpretation, you better to look into mod psi square. In case of what you call momentum interpretation, you better to go for momentum space wave function. We say like that, isn't it? Like that, okay? Yeah. Now look at here, whether all solutions are normalizable. Normalizable means whether we can do this one for all solutions, whether we can do probabilistic interpretation for all solution. No. Suppose if solution is like this, psi of x comma t. Suppose if you are worried about time part, okay, some a e power I kx into e power minus I omega t, kx minus omega t. That's what I was trying to write, okay. If suppose your solution is this kind of solution, okay, try to normalize, try to find a which makes total probability equal to 1. Suppose this range of the function is minus infinity to plus infinity. So try to make one. Mod a square. What is psi star into psi? E power minus I theta plus I theta. E power plus I theta, e power minus I theta. Isn't it? So this will become, speak up. E power 0, e power 0. When you make psi star into psi, can you see this one? E power I theta, modulus values are 1, okay? Yes. So that's equal to 1 dx is equal to 1. What is this integral? Don't write x running from minus infinity to plus infinity, it is 2 times infinity. Don't write like this, this is just infinity. What is this curve? This curve is y equal to 1, am I right? You are integrating from minus infinity to plus infinity, your area under the curve is infinity. Is that okay? So that's why, so this is tending to infinity, that's why look at here, you got this kind of situation. We can't write like this, okay, pure mathematically, okay, we can't write this kind of step, okay. What a that will be multiplied with infinity that can give 1? No a. No a can multiply with infinity, that will give you 1.
What do you think infinity by infinity?
Infinity by infinity is indeterminate. A is 1 by infinity. A is 0, that's what you are trying to know. 0 into infinity. What is 0 into infinity? That's also indeterminate, am I right? 0 to infinity, infinity by infinity, 0 by 0, these are indeterminate. So that's why there is no a which can normalize this one. We call this one as non-normalizable solution.
Sir, actually, what do you think about this infinity? This is like,
No, we don't know about infinity. Infinity means,
because it's a scale, right?
no, in scale, infinity means it is nowhere in our region of interest. Are you getting my point?
We are not
You have some region of interest, am I right? Maybe very large region of interest. So in that region, if infinity means it is nowhere in our region of interest. Particle at infinity means particle vanished. Particle doesn't exist at all. If particle at infinity means particle is escaped, you can't hold the particle at all.
But why we are always then considering minus infinity plus infinity?
No, I mean, this integral also like that, am I right? But it is normalizable. Look at here. Wait a second, I'll talk about that one. What kind of wave function is normalizable, isn't it? That wave function should go to 0 as you make extend to infinity or minus infinity. There should be no probability of finding the particle at infinity or minus infinity. Are you getting my point? If there is a probability of finding the particle at infinity, that means your particle is escaped, vanished from your region of interest. Is that okay? So that's why, look at here, observe very carefully. Mod psi square was constant, am I right? Mod psi square was constant. Constant function is not normalizable. But here mod psi square was Gaussian. This was also Gaussian. This was Gaussian. Gaussian will go to 0 as you move to plus infinity or minus infinity, isn't it? So that's why if your wave function goes to 0 as x tends to plus infinity as well as minus infinity, that kind of function is normalizable because that will have some finite area under the curve. This cannot be drawn, okay? That's why you better to draw mod psi square. This cannot be drawn. This is a complex function. Now look at here. That's why what I'm saying is, for some wave functions, okay, whose mod psi square tends to what you call is finite as x tends to plus or minus infinity. Wave function whose mod psi square diverges as x tends to plus or minus infinity. Suppose if you have a function like this, it is going like this, mod psi square. What is the total area under the curve? Infinity. Isn't it? You can't make total area under the curve 1. You have no choice, okay? If mod psi square diverges, or if mod psi square is finite also, then that kind of functions are not normalizable. Again, you can give some physical interpretation here. Look at here. Mod psi square is finite means, mod psi square is finite at infinity means, you have probability density of finding the particle at infinity, isn't it? If there is probability of finding the particle at infinity, means particle can escape from your region of interest anytime. Particle can vanish anytime and it will go to infinity. If it goes to infinity means it is nowhere. Particle is at infinity means particle is nowhere. You have to understand infinity like that. Are you getting my point? Particle is at infinity means particle is nowhere. You are not studying anything at all. Particle is nowhere in your region of interest. Is that okay? So that's why in this kind of situation we call the wave function is not normalizable, non-normalizable wave function. Not only this, okay? Not only this, if suppose this integral diverges, mod psi square dx, if this diverges, if this happens or if this happens, definitely it will diverge. Are you getting my point? If mod psi square is finite at infinity, definitely area under the curve is infinity. Isn't it? If mod psi square diverges, it is increasing, keep on increasing as you move to plus infinity or minus infinity, okay? Then also definitely this integral diverges. If this integral diverges, then also we call that one as non-normalizable wave function. This integral diverges only when this value is finite at infinity. This value have got some value at infinity. But if you take Gaussian, so it will go to 0 when you go to infinity or minus infinity.
So for the particular region, we cannot normalize it.
No, I mean, if you restrict, again, suppose if you restrict to some particular region, I think any function can be normalizable, isn't it? Even constant function can, or if mod psi square is constant also, in some region you can normalize it one. You should see your region of interest also. That's correct. But here I have taken minus infinity to plus infinity. That's correct. We shall see later. Again, when you do more and more problem, I think you will understand it. Okay. So can you write down some? Now look at here. If integral minus infinity to plus infinity. Okay, you just solved that one. You haven't normalized it yet. Okay. So integral minus infinity to plus infinity mod psi square dx is finite. If it is not diverging, if it is finite, then you can find a multiplicative quantity which makes this integral 1. If this integral itself is infinite, I have shown in the last one, there is no multiplicative constant which normalizes the wave function. If this is finite, okay, we call that one as square integrable function, okay. If this is finite, okay, which we call as square integrable function. It can be normalized. Or normalizable. If this integral is finite, again, suppose if your region of interest is some a to b or something, you take that one. In that region, that integral should be finite. Is that okay, Faisal? Here I have taken minus infinity to plus infinity, most general case, okay? If that integral is finite, we call that one as square integrable function. You have to put this one in a bracket, okay? Square integrable function. If we call as square integrable function, it can be normalized or it is normalizable. That psi can be normalized, okay? That's the idea. All square integrable functions are normalizable. This is not square integrable, okay? This was square integrable. Suppose if you have psi of x comma t is equal to e power minus lambda x square e power some minus I omega t. This is normalizable in the region minus infinity to plus infinity. Get here. This is how we develop in the region, I said.
So it's all about the multiplicity constant.
Whether you can find the multiplicity constant, okay, which makes that normalization integral finite or not. I mean, 1 or not, isn't it? Yeah. Whether you can find that one or not, that does matter, isn't it? If that integral itself goes to infinity, that is non-square integrable, okay, then you have no way to normalize that one. That has no physical significance. Non-normalizable solutions have no physical significance. These are all non-normalizable what you call situations, okay? This has no physical significance. Why? You can't make total probability 1. Then you can't have probabilistic interpretation at all. And also, when that function is non-normalizable, when wave function is finite at infinity, when mod psi square is finite at infinity, then it is not normalizable. If wave function is finite at infinity, means particle can escape, particle can vanish, isn't it? Again, if particle goes to infinity, means particle is nowhere.
This wave function is not solution of the square.
It can be solution. That's why, look at here, my first sentence was, not all solutions are normalizable. You can find the solution. Some solutions are normalizable, some solutions are not. This is also solution actually. Plane wave was one of this. We found this one using this one. Do you remember?
Yes.
Yeah.
There will be solution, but it cannot be normalizable
or non-normalizable. We will have non-normalizable solution also. Not only here, even in case of hydrogen atom, we never think of other solution actually. We think of only one solution. There will be other solution also, because that's a second order differential equation he mentioned. We don't think of that one because that's not normalizable.
Sir?
Yes.
Sir, for normalization limit vary, like minus L to plus L or any.
I mean, this depends on our region of interest, okay? Suppose if you take particle in infinite square value from 0 to a, our this integral is 0 to a. Suppose harmonic oscillator, it is minus infinity to plus infinity. We shall see that one later, okay? Classical harmonic oscillator, you integrate from minus a to plus a. But quantum harmonic oscillator, you need to integrate from minus infinity to plus infinity. Is that okay? Speak out.
Yes, sir.
Yeah, now I'll give some theorems here. What's the time? 7:18. Psi x comma t mod square dx minus infinity plus infinity. Okay. You are integrating with respect to x, isn't it? Huh? Once it's a function of two variable. If you integrate with respect to x, the time variable should remain, isn't it? But usually it will not. If you do this integration, time variable will not remain at all. That means if you take derivative with respect to time, 0. You can show it by Schrodinger equation. This is a property of Schrodinger equation actually. So just check that out, okay? I'll do some other derivation. I'll not spend time on this, okay?
This kind of question as interview.
This is not only interview, this is helpful for some MCQs. That's what I'm saying. That means once you normalize at one instant of time, that again, look at it. We write like this. Here itself, we should be able to say mod psi x comma t whole square dx. You should have asked here itself. It should be function of t. How you have written 1? Can we make it 1 always? Yeah, we can make it 1 always. Because this integral is time independent always. That's why we can make that normalization at one instant of time. It will be always normalized. Normalization constant will not change with respect to time. This is true in case of linear combination state also. If you take non-normalizable solution, don't write this one at all. Write this one only for normalizable solution. Because this itself become infinity. How do you take time derivative, isn't it? Huh? Yeah. Yeah, again, it will be meaningless actually. Okay. If you take, again, that I think he might have mentioned, okay, for normalizable solution, he will start with like that. That I didn't, quoted for, look at here. For normalizable solution, this statement is true. Okay. Yeah. That non-normalizable solution we don't use at all. Okay. We shall see in case of free particle problem, how we can take linear combination of non-normalizable solution to make normalizable solution. Wave packet concept. Is that okay? We take non-normalizable solution, which is a solution of Schrodinger equation. We linearly combine them, and then we generate normalizable solution. That's the basic idea. Okay. So now try to prove this one. He has given that step. I'll try to prove the rest of thing. You can do problem number 1.4, 1.5.